Hello, everyone. Welcome back to the Python Ethereum Discovery playlist. And we today, or in this video, we are going to be taking a look at how a block is validated slash verified. So I did leave the account verification steps in so we can see all the verification at once, just so we can see which functions are used, how they're used, making sure we can trace the values, make sure they're lower than the target hash and everything like that. So we essentially are getting all the values that we can hand trace to see that the target is greater than the actual guess, thus making the consensus valid and making us able to validate and verify both transactions, accounts, and blocks. So we're going to take a look. It's still the same use case where Alice sends Bob a transaction as before. So Alice is the sender, Bob's the receiver. We're sending the same amount. We're going to go through the R, the S, the V creation, everything like that, the sign transaction, and how we do that, but we don't print that out. We're just mainly focused on what parts of the system use consensus when we send a transaction between two users. And that would be Alice sending a transaction to Bob. So in here, we did uncomment or comment out 1, 2. We left 3 and we did comment out 4. So we're just focused on right here. So we don't really print anything out in the main pie. This is all source code debugging. And if we take a look right here, we can see that the only thing we do print out is this star line to separate the parts and the part 3 name. So if we go to run this, we should see the validation of the user, the transaction, and the block itself. So let's run that real quick. Let's see what happens. So we have the private key, which we didn't decode. I guess I missed that in the main. We have the transaction parts. As we can see, we're missing the V, the R, the S, the transaction type right up here. But we see the V, the R, the V, the R, the S right here as before. And this is the reason why we do run it in this environment, just so it'll always produce the values. So when we find the R, the S, the V for one, we can then edit the code, add another block, and then we can trace that R, the S, the V if we send more transactions with that user or to that user. It's just something that's very easy and repeatable for testing purposes. It's one of the greatest parts about this environment. But so this is the account and transaction verification right here. This is all the back end stuff that we don't see in the main code itself. And this is the V, the R, the S, and the transaction itself right here is validated right here. The 22 against the 57 right here. So that's the transaction. So the transaction, the block hash will be different, and the guess for the block will be different than the guess for the transaction. So if we go down here, the part 3, this is all dealing with blocks. So our guess starts with 997, and our result cap, so our target starts with 1157. But if we come down here, we see that 1157 is 1 digit longer. So we can see obviously that the cap is larger than the mining output. Thus, this is valid for consensus to work. And we print out the values down here just so a little bit easier to read. And this is part of the same validation block right here. So this is checking to make sure the information is correct. It's done by the same algorithm as we did for the account. So that's just something that, so if Alice were to send Bob a transaction, these are the things that are these are the consensus outputs for each of the individual asset or facet for it. So we do have the account verification, which can be the 28 all the way up to or the 31 all the way down to the 28. That's the V, the R, the S. So that verifies the account. We verify the transaction right here with the 2241 against the 5789. And since 2241 is less than 5786 in the same length, as we can see, we have a 3, or actually, yeah, we have 3 on each side. I'll try to format that better in future updates. So it can be read up and down. But yeah, this is where the transaction gets validated right here. That's the transaction guess right here, 22418, which is the same as the S up here. I have not found any correlation in the code between the S and the transaction hash. But I'm sure that there's something there. I just haven't stumbled across it yet. There's tons of libraries that this uses, and I guess I just haven't found the right one yet for the proper debugging code. So then after we do the user and the transaction, we come down for the block. So we come down here, this is gonna be the block guess. We will change this and I will run a higher difficulty so we have more guesses so we can see how the proof of work works for the blocks. And we have a result cap right here. So that's the thing we're trying to get under. It only took us one guess. So we only have one output, one mining output against the result cap to compare. And we printed it out down here just for easier readability. So if we do want to change and say, make this more like a real world environment where the difficulty is not one, we can change it up to, let's do 10 first, and we'll go to 100, then we'll go to 1,000. In the code, we only have 1,000 guesses per nonce. So if we go over 1,000 nonces with 1,000 guesses, then we've run out of actual guesses. But so we increase difficulty 10, everything's still the same. We're gonna clear the command line and we're gonna run it again. And this should have more of the proof of work for the block. So this is the system trying with a higher difficulty to validate the block that contains the transaction that Alice sent to Bob. And this is the same transaction we've been running in this main app.main.py or app/main.py file for our demo app. That has not changed. So let's run it again. And this time we have, let's see, 2 guesses. So 10 only produced 2 guesses. As we can see that there's 2 outputs and 2 caps. And this is the winning hash right here. So we have that. Then we come down here. We go back here and we're gonna increase to 100. So we got 100 right there. We're gonna save it. So this can produce even more. And this increasing the difficulty simulates a more realistic world or a realistic real world implementation of an Ethereum blockchain. The current difficulty is somewhere in the millions. We're running it with 1. This makes our validation and verification very, very quick as opposed to the 20 minutes it would normally take on the main Ethereum network. But this is done for testing purposes, so we don't have to wait around to test various values in the code. So if we go back and review to the main code, we're going to run this with a difficulty of 100, and that should produce more values. And that's just because of the way the guesses work in terms of the difficulty. So we're gonna run it again with 100 difficulty, and we're gonna have more outputs. So as you saw there, we have a lot more than the 1 or the 2 that we had before. We actually have a ton. We could go hand trace all of these, but since it's running the same algorithm, we know what it's doing, and we just got to go down here for the winning one and compare values right down here. Awesome. Cool. So we see the max right here. This is your guess compared against the 3752 against the 1157, same length. So 3752 minus 1157 is going to be way larger. So the max, which is going to be our guess, is going to be lower than our target. So then that verifies our proof of work. So something that we can also do to make it even more real world is we can add it to 1,000, the difficulty. So this I do not, let's do 10,000 because I don't know if it will hit on the exact number. So we've now increased the difficulty past what the total guess limit is. So we will break the actual code, the backend code for the Pi Ethereum blockchain. We can see that right here. This will get tons and tons of guesses, but we're working slowly toward a real world equivalent, but on a private network, just to show how long and like how intense it is for proof of work and validation on a blockchain, which goes to how cryptographically secure it is, because they have to figure out this hash quicker than any other miner or validator on the system does. And then when that happens, it will have to check the added block. So it'll expend other resourcing powers there. So we ideally would like a super powerful machine, but with these lower values, it's more even, I would say, in terms of where we don't need a $100,000 laptop or a computer to do the 20-minute block times on the main Ethereum network. We can just increase the difficulty on this network, as well as the source code for guesses, to more match a real world implementation where the difficulty isn't 1 or 10 or 100. It's more of 100,000, 150,000, 200,000. That would give us more guesses and show more of the hashing function and proof of work and consensus together. But we're gonna break the code right here. This is always fun to do. Let's clear it real quick. Run it. So it's gonna run for a while, and we found it without hitting our guess limit. That's pretty cool. So even though our difficulty was higher than our total number of guesses, our total number of guesses was actually able to figure it out before we reached the max number of guesses. So this shows you how even if the difficulty is way higher than what we would expect to be able to reasonably solve, the way that cryptographic functions work, or the hashing functions and cryptographic functions work, is that there's a target bubble and it changed the difficulty, and it's never predictable, but that's something way finite in the details. This is just a more of a testing implementation view of how we can debug the processes within a blockchain, especially during a transaction, a validation, verification of both user block and transaction, and then the adding of the block to the blockchain. In the next video, we will go over the full end-to-end process, but stay tuned for that. And thank you so much for watching. Bye.